Okay, so from time to time you get really accurate message. We made our own Lion King reboot. Yes, so yes, I've done. It's my fault that we didn't see the expected advancement with regards to the cleansing of my body, because I mean probably out of like that's I'm just tired because it's the second night that I haven't slept, and actually it's partly it's actually it's beneficial for the process actually. So but in any way, let's leave this aside. Yes, so we have two containers with germs, and so for now I will disconnect the transformers, and I'll tell you what actually I discovered this night. So I discovered that so I used the mixture from the various aquariums, but it was very clear to me after the process started, an hour or 2 hours or so, that there were all sort of consequences of the various changes, but it was clear that I didn't use the correct commands, and that that what the neurons do was to significantly enlarge the life forms that were there, and possibly creating more neurons, but I think that are not in a complete state, because probably this is related to the fact that I did not connect the actual symbols of the neurons to electricity as it should be, and so so my guess is that they are just duds, even though they look good. They'll probably dissolve. But more importantly, it wasn't my intention to actually enlarge these animals, and when taking into account that I had two containers with the cherubs, the Ark of the Covenants on them. So yes, certainly it's simple that it's like asking to have more of this stuff in my body. This was silly, and I need to actually fix it. But yes, I'm very, very tired, and quite devastated for many reasons, and of course most of all the detachment from my daughters. But it wasn't a bad night from scientific perspective, because it's a setback in cleaning the body, and I will fix it. But I discovered quite a bit of interesting stuff that I don't have the time and energy to show you under the microscope. Maybe I'll do it later. But what I've discovered is that it's actually possible to create very big life forms very quickly, and this is one of the objectives that I wanted. If you remember from the weekend, that we need life forms for the neurons to feed on them. So I wondered, if we can use the mixture with electrolysis and neurons to actually create quickly create maybe biological, maybe carbon based, or maybe other material based. Let's maybe we use the word synthetic, but what does it even mean? But let's say that synthetics means for these papers non-carbon based. So both synthetic and biological, and they can feed on them, but we actually need it's beneficial if we will have large amount of this stuff. And you can create germ colonies, but it takes time. And it was actually proven that very, very quickly, using the mixture from the aquarium, you can create a very dense mixture with pretty big life forms, and non-microscopic life forms. And mostly what was created was string-like, small, very small, worm string-like, or tentacle-like, or sausages. And this is of course related to the symbolic language. And so but they were not microscopic, and I was actually able to I need to wash it because I mean I have so little amount of slides, so I need to wash everything. But maybe you can actually see this here. Yeah, so you see, these are not you can actually, I don't know if you can see, but these are actually not microscopic. You see non-microscopic life forms on this slide. I don't know if it's focused like, I don't have like I rather not like put it under the microscope, but I mean, believe me, I mean, it's you can see, I mean, there are several like big tentacle-like creatures that certainly were created, I mean, during the night, because I mean, they were visible. Just I mean, that it was visible that this is crawling with this stuff, and also my body as a result, which is stupid. But anyway, yes, I mean, it was proven that given the correct command, they can actually work very hard the neurons can work very hard to create life forms. I mean, to enlarge life forms and from existing life forms, which is great because presumably, and this is the next step, we will now see if they can actually eat them very quickly using the electrolysis, and on the way, I mean, both like from the symbolic aspect, reduce it in my own body, and I want to get rid of it, of course, and from the practical aspect, I mean, when they eat this stuff, they have more energy to grow when we want them bigger. And this is very interesting. Another thing that was very interesting to see is that actually they've even created mold in like not more than like a 90 minutes top. I've actually created mold. This is mold. It was created like in an area that for certain, I mean, there was no mold in this area. Like it was created in the most like energetic part, which is like on this is the magnet that you see, the big one. And if you remember, like if you put a rod, one of the rods like just in the middle of the magnet, it's like the electrolysis is very, very strong. So just there, I mean, we created actually mold very quickly, which is, I mean, mold is not created in 90 minutes. I mean, this is like, it's like cartoon mold, but it's mold. And maybe later I'll show you under the microscope. So yeah, the mixer contains a lot of like big life forms, which is good because it's one of the objectives that we set during the weekend, that we need like to be able to get this stuff quicker because it's feeding material for the neurons. So it's not bad, but I mean, and another very interesting thing that I discovered, so this was actually discovered before I actually started the experimentation. So when after like a week or so of the last experiment, when it was actually connected to electrolysis, but probably very soon, I mean, it was just eroded, so there was no electricity, but it was a very long, relatively long, for a week. So I've removed this, I mean, the arc and the thing, I mean, the material that was inside the titanium box was not surprising. I mean, we've seen both neurons as expected, and I mean, and they didn't die, and also life forms, but not much because I mean, presumably they died. I mean, just a small amount because they died from the electricity. And I mean, after that, during this night, they multiplied tremendously and like grew like in cartoonish style. But I mean, before the experiment of this night, I mean, after, I mean, the last experiment, the situation was about that inside we had neurons and not many life forms, and also like remnants of like dead life forms. But what was very interesting, and I didn't see it like immediately, but just on a second look, is that there was actually an accumulation of interesting material outside the titanium box, inside the plastic box that was used as a buffer. It was used as a buffer, but I don't remember that I've actually put water inside it. Maybe just a little bit, and it's all evaporated because it was very hot week. But it was not. It didn't look like water. It was very brown. Now it's actually a little bit changed during this night experiment. But it was very nice. I mean, it was very. I mean, interesting material, like mixture, because it was brown, but I mean, almost like, I mean, smooth, like without like all the shit that is like, I mean, so common in like when there is biological or synthetic life forms they are present with the neurons. So it wasn't like that. It was like brown material that was it was like a jelly, and also the texture was great. I mean, this is exactly the kind of like mixture that I actually want to produce. That, I mean, there should be like I mean, not very dark, and they should be like without all sorts of like I mean, it should be like as smooth as possible and like jelly mixture. This is the, I mean, this perhaps, I mean, it's one of the greatest, I mean, from texture perspectives, and like, I mean, because I mean, this all of those things actually affect like the efficacy of the electrolysis, especially when you want to create like complicated objects. So actually, so yes, I mean, of course, I took a sample or two, I mean, and watched it under the microscope, and what we've seen is that this is actually a mixture of neros, tons of neros, like millions, very small ones, just perhaps like just a few were large, but mostly very, very tiny. I mean, I'm not tiny. Sorry, no. I mean, the smallest ones that you can actually observe using 64 magnification. Of course, if I use 1500 magnification, which I can also do, I mean, they will not look tiny. But I mean, in my lab scale, all of them were very, very small. I mean, which was and which is not like characteristic, like in the titanium, like the Titan like container experiments. Mostly you see many big ones and small ones, but there were a ton of very small ones, and they were actually not that, but real ones, because a week was passed. So I mean, that's, I mean, the ones that are created but not completely created, or they just die after a while, they do it like very quickly, like after a day or two, not after a week. So if they survive for a week, it means that this mixture, this brown jelly, actually contains millions of very small like viable neros, which is great. So the question is, and almost no life form at all, which is excellent, because I also need this as well. No life form at all. So what actually happened here? I'm not certain, but my hypothesis is that what was happened is that actually there was nothing inside like the white container when I conducted the experiment. Perhaps just a little bit of water that was evaporated, I mean, from the heat this week. But it wasn't sealed, if you remember. I mean, we had the Ark on top of it, but none of it was actually sealed. And we've seen so much like dehydration, like, I mean, with the content that was inside this container. So what I think that actually happened is that, like, I mean, it's for certain. I mean, a lot of water was, I mean, was like, dried during this week. This is the fact. I mean, because I mean, we had like, I mean, a week ago it was like a lot of like, I mean, the liquid level was high, and after, I mean, a week when I opened it, I mean, it was almost just wet, but I mean, no liquid at all, almost no liquid at all. So yes, I mean, almost all the water evaporated. But what I think that happened is that it evaporated, but it like I mean, some of it just got stuck in the bottom of the ship, like the glass ship of the Ark, of the with the curb slash, like, I mean, like cubes, or like A.G. Wells style, like tentacles, like monsters. So, and then it dropped like part of it, I mean, again, I mean, to the container where it came from, and then evaporated again. Part of it outside and then evaporated, and we lost it. But some actually dropped inside the outer container, because I mean, the ship, I mean, was like that. I mean, it covered like this. So, and then this part accumulated in the outer container. Now my hypothesis, and I mean, it's difficult to prove it, but it makes sense, is that we had so much small ones because probably the small ones, I mean, were lifted by the water, by the evaporated water drops, and probably the bigger one just cannot do this trip, like, because they stay like on the ground. And if it's true and it sounds like reasonable, it means that we have another like way to actually do something that we were interested in, which is to like separate the neros from the biological life form. Because yes, we can do it by just storing electrolysis, and this is a viable option. But the problem with that option is that you get like a very dirty mixture with like all sort of like ton of dead biological material. It's not a huge problem. It's also a viable option, but this option that we've seen now is much better, because we get a much better, I mean, mixture. Because again, I mean, the mixture that is like almost smooth and hard, like jelly, and without also like debris and like and translucent, is the best like kind of mixture. I mean, this is the ones that I actually try to produce, like exactly this one, because they are both very conductive, but they are not burned quickly, and they do not, and there is not a lot of water that creates fumes that create all sorts of like problems with the electrolysis, and also it's the fact that it's smooth helps with the symbolic language, and so it's very and of course we don't have the life form which could be in extreme cases like today, it creates life forms in my own body, which is like very shitty. So, but even in non-extreme cases, usually you don't want the life forms like, when you try to create like, I don't know, rings or like diamonds or gold or whatever, or pharmaceuticals. So, so how can we actually leverage this knowledge to do it like, not by chance? Yeah, Israel is a very hard country, but I hope I will be rescued from this Nazi hell, and maybe, not to a very hard country. So, of course, we can just hit it, but we need to do it very carefully, and I don't have the means for that. I need to see how I can, because I'm not going to do it in the kitchen, of course. I need some kind of, like a portable stove, which I have, but I need to ask my mother to bring it to me. So maybe with the portable stove with very, very gentle fire, because we don't want to burn anything. Maybe very gentle fire will actually, artificially, evaporate like water from a mixture that contains both neros and life forms, and then we can catch it like in a similar way to it was done like that here, but by chance, and catch the material, and then we will have like this very rich, like jello, like brown jello, which is great. Of course, there are still two questions left. First, okay, but you only have the small ones, and you want the bigger ones. But yes, but so maybe this process could be actually perfected, that also the bigger ones will take this air lift, with the evaporated like water drops or liquid drops. We need to think about it. Although the small ones are also very even if it's just the small ones, it's still a very a viable a process that should be it has its place in the toolbox, I would say, of the alien alchemist. And so, and the second question is, of course, how so many of them were actually created. But this is probably due to the fact that it was weak. Even if it was not connected to electrolysis throughout all the time, but a week is a lot of time. We used very rich mixture. We used mixture from the aquarium, which contains considerably more neros than we were used to. So it's not that such a surprise that they created a ton of neros, and using them in the explanation of evaporation and then condensation back to the white container, the external container, we can understand why we had only small ones. This is all very interesting, but I want to get rid of the stuff from my body. So what I'm going to do now is actually to replace the mixture. I'll take the mixture from the outside, and presumably it still doesn't contain a lot of life forms. I'll just validate it under the microscope. And I'll take this relatively pure jelly and put it inside the titanium container after I wash it, of course. And the inner stuff will be placed outside. And presumably this will signify, my body is of course represented by the inner container, not the outer. The outer one is mostly used for water, like to cold water to make to keep it cool, like the electrolysis chamber. Now that I've discovered that it's also potentially another usage, I'm using 3 containers, as you see. The titanium container, the ones that presumably used for evaporation, and the outer one with cold water. By now it's not that cold. I need to replace it with ice cold water. So that's what I'll do, and hopefully we will, the best case scenario, we will actually get rid of the stuff from my body, and also we will have the neros in the outer container will eat these germs. I just need to use the correct commands, and maybe they will actually use the energy from the food to go, which is great. Now another question is, where do you actually put the rods of the electrolysis? Do you put it in the inside or the outside container? So until now, I almost always put the rods inside, because the inside container was the important one. But of course, there are also for the limitation of when you use the inner container, and there are actually many advantages of using the outer container for the electrolysis. This is, of course, if you remember, this falls under the category of energy transfer, which is kind of like science fiction, like hardcore science fiction, but it doesn't necessarily need to be, because this kind of energy transfer, of using electrolysis on the outside, can be explained like by just, very simple physics, like if like a rod here, like the hot rod here, and the neutral rod here, for example, and it's quite like 30 volts is quite high, relatively high for DC charge. So the current can flow like surrounding the titanium, inside like the mixture on the outside, but it can also flow like do half of the way inside the mixture, but they take like a hitchhike, using the fact that this is metal, so it's highly conductive, so it couldn't like first it will need to to push its way through the liquid, of course with the help of the needles, and then it will take very like fast way here, and then another like slow or like highly resistive, relatively resistive like push to the neutral rod. Okay, so what would be the benefit of it? Just flowing, in the body of the container doesn't help us at all, and this was established long ago, because both by experimentation and also by theory, because electricity flows through the least like resistant like path that it has, but you actually want to use it. But maybe, and this is where like the science fiction gets into play, but it's very mild side. Or the opposite is actually true. It's hard science fiction, which means that it's very close to our reality. It's not energy transfer in the way that I've used it until now. It's not. That you don't need to entirely change physics in order to understand this kind of energy transfer. But so my thought is that this. The inner container supposedly also contain many mirrors, so they can form chain. And if they form the chain from here to here, first it will be actually like shorter than like half the circumference. It's like shorter by factor of pi divided by 2. Okay, like 1.7 shorter. Times shorter. But also it can have much less resistance, because this is metal, which is it doesn't have resistance, but the neurons are presumably they are superconductors, so presumably they can have even like better like alternative for the current than taking this hitchhike on the surface, like on the walls of the container. So I'll test it now, and it's not. I think it's going to be interesting. I would say, I'll take this opportunity. I'll finish this video with a word regarding superconductors. So many people ask about it because I guess it's something that is very sensational, because it's like in all sorts of like movies we have like vibranium, like in Wakanda, like or like the stuff that the Wolverines are like shield is made of. I don't remember. And you have plutonium, all sorts of, and the stuff that, the shield of Captain America is made of. So in popular culture, you have the issue of like alien materials that is very, it's very exciting. So yes, people think, so people ask, of course, we should just, be more accurate. Superconductors are known more than 100 years. The issue is that this is presumably a superconductor which is stable at room temperature, which is something that is not known to humans. Like, it's only hypothesized that maybe it exists, but this is something that is not known to humans at all. This is really magic material, like from comics. But there is a question is whether it is a superconductor, because this is only a conjecture, or a theory. But how can we actually prove or disprove it? So I would say that it's very difficult for me to prove or disprove it. When I don't have any laboratory and no money at all, in these conditions. But I would also argue that it doesn't matter all that much as you can assume from the first glance. Because I would say that, the question is, why do you even need. Besides the fact that it's amazing that material that was not known to humans actually was discovered, and it presumably it can like clone itself very easily, and so it's amazing stuff. But let's ask that practical question of like, why do you even need this room temperature superconductor? So I admit I don't have the complete answer, and in order to actually like answer this question like in like very like in exhaustive matter, you need to study physics more than I have, like, and maybe I should do it, but as I said, I mean, I don't have much motivation because of my bad mood, and if I actually like have the mood to actually watch YouTube physics videos, it will probably be in the subject of like basic electricity, and like which for me is much more important now than thinking about superconductors that are, they are much, it's much like, from science perspective, it's much more important, but I don't have the capacity to actually do anything with it. But I would say the following. We don't need to understand the entire theory of superconductors to understand that, in a very basic way, superconductors are so beneficial to humans. Also now, they are used, more than 100 years, because, they have all sorts of like very interesting properties. And again, to give an exhaustive answer, you need to study physics more than I've had, and so I cannot do it. But what I can say with my limited knowledge is that probably the most basic characteristics of superconductors is that when like the electricity flows through them, they do not lose the energy to heat, which is true to every material that is not a superconductor. So they can use all the energy, the electrical energy, to actually perform work without radiating heat. And this is in itself, it's very, very beneficial, because as anyone with just a basic knowledge of engineering, not even physics, but just engineering, anyone that has some background in engineering, almost any kind of engineering, maybe not software engineering, but any kind of other engineering, they know that the issue of heat generation is both very basic, in all sort of in motor engineering, and machinery engineering, but it's both basic but also always prevalent. It's basic, but it's always there. Specifically, for famously for CPUs, for computer, central processing units, it's the main issue, for, I would say, maybe 20 years. The main issue is how you not lose heat, energy to heat, and on the way, need more and more, and this, the heating is, then you need to cool the CPU, and it's not, you can't always do it, so it puts the limits to how fast you can actually work. And also there are more modern issues of environmental issues, because during the last decade or so, it became evident that heat from CPUs, which in the past was so to be negligible and no one cares about it, but it's now it is now known that it's actually starting to actually create impact on the environment, and because there are so many of those in cloud environments. So this is very basic. It's very it can be very, very beneficial for all sorts of reasons. Both for many engineering and also environmentalist reasons, to have a material that does not lose energy to heat. Now, we already know that those neurons, they work. They for certain, they do not. We don't know if they are superconductors, but we know that they lose very, very tiny amounts of energy to heat, if at all, because of the fact that they create huge construction works in relation to their own size, without dying in the process by melting. Because normally you would expect, for such small resistors that create so much work, to actually, even if they produce small amount of heat, they would melt by the process, and they do not melt actually they do not melt. I mean, eventually they melt if, I mean, it's the, like the, if like it's the environmental condition is, I mean, of the electrolysis, I mean, is too hot, but they do not melt by their own work. They melt by the fact that the mixture itself is getting too hot by other reasons, like separation of like a molecule to atoms or other molecules, all sorts of things related to electrolysis, or maybe, I mean, the other like materials, like in the construction, like maybe the rods, the metal rods are getting hot, and maybe they heat the mixture, and so this could also, I mean, be like death by heat, I mean, for the neros. But they do not die by their own work, which means that, and they work with amazing capacity. We've seen them like creating like huge mining like work, if you remember. Like, I mean, the entire slide was filled with millions of like tiny sellotape, like, I mean, like thin duct tape, like chunks that look like small diamonds. So they made huge amount of work in a small amount of time, and they do not die from the heat, which means that I would argue that de facto they are like superconductors, like room temperature. Okay, maybe they are not. Maybe it will be discovered that they are not perfect room temperature superconductors, and that, I mean, that they lose some energy to it, but it must be very tiny amount because of the fact that they stay alive. And also there is a very, very good possibility that this actually is, I mean, related, I mean, the amount of energy that they lose actually related to the temperature, which, I mean, so maybe you can say that they are, in that case, that you cannot say that they are perfect room temperature superconductors, but I mean, we've already seen since like the beginning of this research that they work great in the freezer. Like, I mean, unfortunately I don't have like a freezer in my room. If I had money, I would probably buy like a small freezer for my room to hold experiments in it, because I mean, it was demonstrated long ago that it's a great environment like for them. So maybe they are like, I mean, freezing in the freezer they are superconductors, which will also place them like in imaginary like tier of like the material tier list, because like normal superconductors that are known to humans need to be like kept in temperature that is not just, I mean, the normal temperature that you have in freezer, which is like -20 or Celsius. I mean, according to my knowledge, they should be kept like in much lower temperature, and that's what makes them so difficult to handle, because like keeping these materials that are, as I said, they are known to humans more than 100 years. It's not that they are not known, but keeping them like in very low temperature requires a ton of energy. So it makes like the whole process, I mean, not worse. Sometimes it's worse. It's still, I mean, they're still used. So in some like scenarios, I mean, even like after the huge spending on freezing on modern freezing, keeping like, I mean, very low temperature of the material, it's still beneficial. So they are still used. But I mean, of course, it hinders the construction, because when you need to maintain like very low temperature, I mean, you cannot do everything that you could have done like without this limitation. And so, I mean, even if they like the neros like show their like superconducting property in like when they are inside the freezer, which means -20 degrees, or just a cold day in Russia or Norway. I mean, so it's still amazing because it's not known to humans. But I would argue that, I mean, I'm not sure that it even does matter to that matter. I mean, because the fact is that they can walk and not lose energy to heat. So if we actually found out that they do lose, maybe in room temperature they lose a very, very tiny negligible amount to heat, they would still be incredibly like useful, because of the things that they actually do. So I mean, from that perspective, and yes, I mean, I'm only speaking about one perspective, like of superconductors, which is not like losing the energy to heat, but it's a main like property of superconductors. And I said again, I cannot like deal with the subject like in exhaustive manner, because I elect theoretical physics like study that I should study more theoretical physics in order to understand this issue, which is a complicated one. But even just, I mean, the basic property that was already demonstrated so many times is enough for, I think, to say that they are practically superconductors in room temperature, even though they might not be perfect superconductors. Like maybe they do lose in room temperature, maybe they're like in low temperature, but far higher than the temperature that is used with non-superconductors. So it's much easier to maintain this temperature, because you understand that maintaining a temperature of minus 20 degrees is much easier than doing it in like minus 90 degrees. So and even just by keeping it in room temperature, which doesn't need any consideration, they still show, maybe they show like perfect behavior of superconductors. This should be like proven, but even if not, they show enough properties of room temperature superconductors in order for us to say that they are practically that's what they are. And I mean, that's just another reason why they are so beneficial and so valuable for any like sentient beings that want to create anything, that construct anything at all. Okay, so let's start the work on this titanium and the plastic containers, and also hopefully it will like help cleaning my body as well.